And we are live. Okay, so yesterday we talked about your redundancy formula to find out how many lines you needed to remove to make it a spanning tree. What was our formula?
Edges minus vertices. Edges minus vertices plus 1.
Fantastic. Edges minus vertices plus 1. So I know we did this one yesterday, but I want to start here before we jump into example 2. So example 1, we found out edges. How many edges did we have in this graph? 8. 8 edges minus how many vertices?
8.
Plus 1, which means we had a total of 1. We had to remove 1 edge. Okay. We then said, how many possible spanning trees exist in this graph? Well, I've got one circuit with 3 edges. I can remove any one of those 3 edges, and it now becomes a spanning tree. So I had 3 options. I could remove C and D,
CH,
or C and H, or H and D. Okay, this is the simple one where you only have one circuit. All right, flip your page.
Hold up right quick.
Well, since you weren't here, you're actually going to take your notes.
You know what? You can just go ahead. I just watch all of them.
You know, watch all my videos and catch up.
Yeah.
Okay, so example number 2. We're still going to use that same formula. So redundancy equals, how many edges are in this graph?
9.
I've got 9. 9 edges. No, minus. What am I doing? Minus, how many vertices do I have?
8.
8 plus 1. So how many edges do I need to remove?
2.
2. I need to remove 2. Okay, notice I have more than one circuit this time. So I need to remove an edge from this circuit to break it up. Okay, so again, you had 3 options. I can remove CD, CH, or HD. When I remove those, I still have to remove a second one. I need to remove a second edge from this circuit. Okay, so if I remove CD from my first circuit, I then have to remove 1 from my second circuit. So I can remove CD and DE. Yes.
So it can't be from the same circuit.
No, you want to break up all of your circuits. Your goal is to break up all of your circuits. You're going to break up 1 from each one. So I can do CD and DE. I can do CD and EF. Okay, that's another line from that second circuit. I could do CD
FG.
and GF or FG. It's the same thing. It doesn't matter which way you write it. Or I can do CD
GD.
and GD.
You already know, man.
Okay? It's going to be the same for each column. Okay? I can remove CH. And if I remove CH, I can pair that with DE or EF or GF or GD. Okay? Does that make sense? Why you have so many options? Okay. I can also remove HD from the first one. And again, I can pair that with a removal of DE or EF or GF or GD. Okay. So this is one way to get all of the options that you have. So this entire chart here is your options. So there are a total of 12 spanning trees in this picture.
Hey, I would have never guessed it.
This chart can become very difficult to do, especially when you're spanning trees or when your diagrams get really big. So we have a second method. Do you remember back in probability? If I told you you had 3 shirts and 4 pairs of pants, how many different outfits could you have? 12. How we get that?
4 times
You
3.
multiply 3 times 4, 4 times 3. It's the same thing here. So I've got circuit 1. If this is circuit 1 and this is circuit 2, how many edges do you have in circuit 1?
3,
Times
4,
how many edges do you have in circuit 2?
4.
4.
That's 12.
And that gives you 12.
Oh, snap.
Dang, so that's the shortcut right there.
That's the shortcut.
Jeez, I like it.
Say no more.
It's not telling you what you're removing, but it tells you you have 12 different options to do so.
Wait, those are edges, right?
Yes.
You know this is GD.
Oh, yeah?
Yeah.
Fantastic.
Remember when you threw a bloody hit that one day?
Huh?
When DeMarco was here? Remember when DeMarco was here and he did like this?
Oh.
Good call.
Okay.
But Mike, are you repeating?
Okay.
I was out.
How many edges do I need to remove in example 3? Again, go back to your redundancy formula. Redundancy equals, how many edges do I have in this graph? 9?
It's the same graph, just about.
Almost.
Ooh, you need to remove 2.
Minus 8 plus 1 means I have 2 that I have to remove. Okay, so same kind of idea. I've got 3 options in this circuit. So I've listed them, CD, CH, and HD. Along with those, I can pick any one of these 5 edges. So I can pick DE, or EF, or FG, or GH, or HD. Okay? Watch what happens. We're going to fill these in. It's the same exact thing. I can match CH with any of these 5 options.
For real?
I can match HD with any of these 5 options. Mr. Range just said there's 15. There's only 14.
Why?
You tell me.
I didn't know to keep it balanced.
Because
that one shares a
like
line.
What?
Here's a line.
It shares a line. Look right here. If I remove HD, I can't remove HD again. That doesn't work.
Oh, yeah.
So you only have 14 instead of 15. You can't remove the same line twice.
About that.
So I have a shortcut for this as well.
Yeah, just ignore it.
Okay, what's something else? Thought we were cut. Oh, you did good. Oh.
So just like we did the last one, how many options did we have in circuit 1?
About 3.
3. How many options did we have in circuit 2? About 5. Okay, the way we get rid of the fact that that is overlapped and I've counted it twice, because think about it. If I count 3 in circuit 1, I've counted HD. If I count 5 in circuit 2, I've counted HD again. I don't want to count it again. So the way we do that is we're going to throw this in parentheses and subtract 1 on the inside to get rid of the fact that we've repeated it.
Oh, that's good.
So 3 times 5 is 15, minus 1 is 14. Okay. That's only if they share a line in common.
So if they don't share one, use the first
You
one.
just take how many edges in the first circuit times how many edges in the second, how many edges in the third, if there's 3 of them, and just multiply them together. This only happens when they share an edge. So let's use this to practice. Okay, so the easiest way I found to do this is 1, find out how many circuits you have. 2, identify them and tell me whether they share anything or do not. So number 1, How many circuits do I have in number 1?
One.
1. That's it. I've got this circuit right here. How many edges are in that circuit? You have 4 spanning trees.
Oh, that's big.
When there's only one circuit, you only have those options.
Wow.
Just like when we did, not that one. Just like when we did this one, and we only had one circuit here. We had 3 options, each one of the individual sides. That's what that is. Okay? Number 2, how many circuits do I have? 2. I've got 1 here and 1 here. Do they share a line in common?
No.
No.
Oh,
No.
never mind.
Okay, your circuits aren't fused together. So all we do is find the edges and multiply them together then. Circuit 1 has,
4.
4 times 5.
circuit 2 has 5.
20.
You have 20 total spanning trees.
20.
Number 3, how many circuits do we have?
2.
2.
Do share a line.
This one, they do share a line in common. So you need to automatically put your parentheses.
3 times 1.
4 times 3 minus 1. There's 11 different options for spanning trees for that one.
It's 4.
It's looking easy.
Okay. Number 4,
No.
how many circuits?
4.
There's 4. 1, 2, 3, 4. Do I have any circuits that share anything in common?
No.
Yeah. 3 and 4.
3 and 4. So this grouping will need to go in parentheses when we get there. So circuit or edges in circuit 1,
4.
4 times edges in circuit 2
5.
times. Now these 2 are grouped together, so they go in parentheses.
Wow.
How many in circuit 3?
3.
Oh, 3.
How many in circuit 4?
3. Minus 1.
Minus 1.
I do -1.
Sharing one.
Because you share an edge. So when I count these 3 edges and then count these 3 edges again,
Oh, yeah,
I've counted that edge twice.
Would that be
So you want to
160?
subtract 1 to get rid of it.
Would that be 160?
Okay? Good. There should be 160 different options.
Well, I'm on the ball.
Alright, hold up. Before you do anything else.
Oh, you need to calculate.
My boy, Trey came.
Pretty today.
Right.
The interview.
It's like a church boy.
Interview.
Wrong.
Okay? Over here, how many circuits do I have? I've got 4. 1, 2, 3, and 4. Okay? 1 and 2 share an edge in common, so they're going to have to go in parentheses. 3 and 4 share an edge in common, so they will also have to go in parentheses. So, let's do 1 and 2 first.
3.
Edges in 1, 3 times
5 minus 1.
5 minus 1. Okay? The second one, how many edges in 3?
4.
How many edges in 4?
3.
Minus 1. So this is technically 14
Times 11.
times 11,
154.
which is what?
154.
There's 154 different options. Okay. The biggest thing is remembering when they share a line in common to throw those in parentheses and subtract that 1. Okay, 2 more. Number 6, how many circuits?
3.
3. Do any of them share anything in common?
No.
No. So, circuit 1 has
4.
2,
3.
3,
6. 72.
72. And finally, number 7, how many circuits do I have?
4.
4. 1 and 2 share a line in common, so they must go in parentheses. 1 has,
4.
2 has,
4. Minus 1.
minus 1. Times 3 has,
4.
4 has.
5.
Okay, so we get 15
300.
times 4 times 5, which is 300. Question.
That is about easy.
There's an advanced one at the bottom.
Let's do it.
Yeah. That is bonus if you can figure it out.
How much?
I have yet to have a student figure it out.
How much bonus?
I'm gonna figure it out right here.
10 minutes.
Think about it.
It can't be.
Okay, let's get through what else we need to get through, and then you guys can ponder over that like third block did. I can't pause the recording and then restart it, so we need to do this now. Okay, so the last thing we need to talk about in this section, 7.3, is Kruskal's algorithm. So our goal, we said, is to find the most optimal tree. So we call that a minimum spanning tree. Okay, so this is specifically a spanning tree with the least weight. Okay, we just got done talking about the fact that you could have 160 different options for a spanning tree. You could have 152 different options for a spanning tree. How do we then go about finding the shortest or the least or the smallest spanning tree? Okay. So, review of what we just did. In network 1, how many possible spanning trees do I have? Just like we did on the last page. So how would I do this one? I want to know how many possible spanning trees, where you told me how many edges each one had and found out your total possible. So, how many circuits do I have?
2.
Do they share a line?
Yes.
Yes, so they must go in parentheses. 1 has how many edges?
3.
2 has? -1. So you have 14 options in here. Okay, network 2. You have how many circuits? 1, 2, 3. This one shares in common. So we should have 3 times 3 minus 1 times 4. So 8 times 4, 32 options in this one. This last one, I have 4 circuits. 1 and 2 share a piece in common. So 4 times 3 minus 1. And 3 and 4 share 1 in common. So 3 times 4 minus 1. It's 11 times 11. Okay. So I have 121 different options. That is a lot of options and a lot of ways to do things. So they came up with something called Kruskal's algorithm. Okay, please understand, this is very similar to cheapest link, but you only have one role in this one. You cannot create a circuit. Okay. It doesn't matter how many lines you have coming out of a dot anymore, throw that out the window. Okay, all you need to know is you cannot make a circuit. Okay, also, rule number 2 says, stop once you've chosen n-1 edges. Remember, we talked, if you have 7 vertices, you should only have 6 edges. Your edges should always be 1 less. Okay. So, I've got 3 examples, and we're finished. So, the way I start you out with Kruskal's algorithm, first off, this graph on the right here is the graph that goes along with this map. Okay. So don't let that confuse you. Remember back in chapter 6 where we did the real life stuff and we drew the pictures that went with it? That's what they did here. So you always want to start out with how many vertices do you have in your graph?
7.
There are 7. If I have 7 vertices, how many edges do I need to create a tree? 6. Always 1 less. So I need to highlight 6 lines. So let me get my highlighter here.
All the way around.
Give me a minute. All right, grab a highlighter if you want one. Okay, so just like cheapest link, you want to start with your smallest edge. What is my smallest edge in this graph? 42. So we highlight it. What's my next smallest edge in my graph?
45.
40. Smallest edge. 49.
You wanna go to 74?
What's my next smallest edge?
Oh,
51.
53.
Not that one.
Okay. I've got one that connects B to A. Can I use that?
No.
No. That closes a circuit. But Notoria said I can use this one over here.
thought you couldn't use that one,
Why?
because it was 3.
And I just told you to throw that out the window. The only rule with this one, which is why everybody gets confused. Kruskal's algorithm, it does not matter. You can have 17 lines coming out of a dot. Does not matter. Okay, your only role in Kruskal is the fact that you cannot create a circuit.
So you go to 53?
So we can do the 51. You said then I can do the 53. Yes. There's 5. I only need one more edge.
86.
Can you do 55?
So,
You have
No.
to do 59.
You can't do 56 either because then that creates this 4-edge circuit right here. So we'd have to use 59. As soon as you reach that 6th edge that you tell me I need, you're done. The last thing you need to do then is add them up. 59, 53, 45, 49, 51, and 42. They got last period. You sure? They could have been wrong last period.
Oh. Absolutely.
Did you?
Yeah.
What? I like Kruskal's algorithm. The problem I found though is people get it confused between cheapest length and Kruskal's. And it's all because of the 3-edge rule.
299.
$2.99. Okay, so your minimum spanning tree has a weight of 299. That's it. Okay, so what are some positives that you see so far of Kruskal's algorithm?
You can use as many edge lines.
It's easy.
No, you tried to go.
Right.
Trey's getting all deep over there, like. Okay, Kruskal's algorithm is super easy. Okay, it's fast.
Affordable.
I wasn't going affordable, but I was going optimal. Okay, you will always have your smallest spanning tree if you use Kruskal's algorithm. Always.
I really want affordable.
You would. All right. So we've got 2 more examples and we're finished. Yay. So the first one on the left, how many vertices do I have? 5, which means I need how many edges? 4. My goal is 4 edges. So let's see. What's my cheapest?
1.2.
1.2. There's edge 1.
1.4.
There's edge 2.
2.1.
There's edge 3.
2.2.
There's edge 4. That one was easy. You didn't have to skip over any. Okay. And again, the last thing you need to do is add up 1.2, 1.4, 2.1, and 2.2. Your MST has a weight of 6.9. Yes, ma'am.
Do you have Alexis Oyoki?
I do.
Can you send him to the office?
Sure.
Thank you.
She sounded remotely happy.
Are you leaving, my friend?
When she get promoted,
Who was that?
She assistant, Rebecca.
Are you serious?
It's what I used to do. She wore long skirts, a little short. It's what I used to do.
You know what I'm talking about? Brito.
You know what I'm talking about?
You talking about
Same
Rebecca
car.
Brito?
Yeah, that's her. Yeah, say her name. Rebecca.
Brito?
Yeah, that's her cousin. Her cousin.
Let me know big thing.
Exactly like that.
All right.
That's her name.
Second graph. How many vertices do I have?
Yeah.
I have 6, which means how many edges do I need this time? 5. Let's find them. What's my first edge?
5.
it's 2-5.
You can use both of your 5s. That's okay. What comes next? 10.
47.
What comes next?
15.
20.
Wait.
15.
15.
Oh.
Okay. 15 connects these two. Okay. Now you said 20. Which one though?
A to E.
A to E. Why can't I use E to D? It closes a circuit. Do we have 5 lines now?
Yes.
We're done. Add them up. Move on with your life. 5, 20, 15, 5, and 10.
We did 5,
5, 5, 10, 15, and then the 20. Your MST has a weight of 55. Are there any questions from 7.1 to 7.3?
No.
Oh.
Yes.